You got a question, or you just saying yourself? All right. Any questions over homework?
You just said it was a stream.
No. Okay. Last class we were learning about I, so like me, but I, which may be called J in a later class, depending on if I has already been used. Because you already used I as the area moment of inertia, and now it's the mass moment of inertia, so if you need both the area, second area moment of inertia and the mass moment of inertia, then I already was taking C. That's more mechanical issues than civil engineering. So last class we were talking about calculating, we should be able to calculate the mass moment inertia for any object. How did we do that? If you have a general object, what is that? It's the dm r squared, the integral, the surface integral. And then you could either use disks or rings when you do the integration. So we had the parabolic and things like that. If we already know, based on if we have the things in the table, then we can use what? If we have two different objects, how can we combine them? Use a parallel axis system. Theorem, so it's mass times r squared plus the I about the center of gravity. And then radius of gyration, what was that? So basically your mass times k squared is equal to I. It's an easier way to think about it than the square roots of that. So it's basically where all the mass is, it's just you put all your mass at a certain distance about the rotation, and then it's equally as hard to rotate about that point. Today we should be able to apply Newton's laws for rectilinear and curvilinear translation. What does that mean? What does translation mean? We're not moving. So we're basically going back in time, but now we need to figure out, well, what the moment is going to be so that we're not moving. We ignored that moment before in the past. And so we'll basically look at our free body diagrams and go from there. So we have the wheelie, the guy doing the wheelie, so you can figure out what the acceleration is necessary so that the front wheel comes off the ground. That's how we can use that. So, general, when a rigid body undergoes translational motion due to external forces, the translational equations of motion can be expressed for BB. Sum of the forces equals mass times acceleration. Answers. If you, okay, in chapter 13, the answer was all of the above. Or we move beyond chapter 13. Right? Because in chapter 13, we're treating it as something as a point, and so therefore we couldn't have any moments on our body. And as soon as we start having you apply moments about our body, that is how much weight is going to be on the front wheels, how much weight is going to be on the rear wheels of your car, then the equation, sum of the forces equals mass times acceleration. That acceleration is going to be your center of mass, which is B. So B is the right answer for this chapter. F is equal to ma works for any single point, but it won't work to calculate the resulting moments. And so now F is equal to ma, and that A is the center of mass. I'm not going to mark it wrong if you didn't do it. How about this? The rotational equation of motion about the mass center of a rigid body indicates that sum of the moments due to external loads equals you found your clicker? All right. So sum of the moments equals IG alpha. We don't have MA in our equation. So sum of the moments about the center of gravity is equal to IG alpha. We'll have an R cross MA if we have it around a different point other than P. And so in this case, the answer is A. So when would we use this? Well, translation here, we have the boat's translating. We apply a certain tension on our trailer hitch. We need to figure out what's the normal force at A, what's the normal force at B, what's the reaction force is going to be. And here's where you apply MAG at the center of gravity. It would have a certain height, and basically you don't want your boat to fall over. So how many equation motions do we need to solve the problem? What unknowns do we have? We know the tension. We need to find MAG and NA and NB. There's 3 unknowns. So therefore we need 3 equations. So we have the sum of the forces X equals mass AX, and the forces Y equals mass AY, and the sum of the moments about any point, or sum of the moments G is equal to IG alpha. Tractor, here we're raising our box. If we raise it too fast, it's going to slide off the end, and then we break whatever's in the box. So how fast can we do that, given the fact that we know what friction is going to be? So in this class, we're limiting our discussion to planar kinetics as well. So we don't have any fun stuff with the gyroscopic moments, things like that, because we only have a certain amount of time this semester. The gyroscopic stuff is a lot of fun. You get to play with yo-yos. And why does the yo-yo not twist when you twist? Things like that. Beyond the scope of this course, but it's still a lot of fun. So in general plane motion, we said it was a combination of what? Translation and rotation. So any single motion you can describe as translation and rotation. And whenever we're rotating, we're going to have what? The acceleration of A with respect to B or B with respect to A. That's going to have 2 components. Normal is R omega squared, opposite direction of R. Tangential is R alpha, and that's perpendicular. So those are the 2 things. That's chapter 16. Now we're going to figure out, well, what forces are we going to apply on our body such that we get the acceleration, or if we apply these forces, what's the acceleration are going to be? So we basically set up a coordinate system that based on point P, and your axes need to be rigid. So they either need to be fixed or translate with a constant velocity. This is an inertial coordinate system that is a coordinate that's not system that's not acceleration. Is the Earth, so is this an inertial coordinate system? Fixed. It's fixed to the edge of the Earth, but the Earth is spinning around, and so we're going to have other accelerations. So this actually isn't an inertial coordinate system, but it's close enough that we can get reasonable answers. Right, but the Earth is spinning around, so we're going to have an R omega squared acceleration towards the center of rotation, which is not quite straight down because we're not at the equator. It's actually, I have no idea which way to write. Anyways. That acceleration is small enough that we can basically neglect it. But inside your car, as you're turning a corner, you can't, even though your coordinate system is fixed inside your car, since your car is accelerating, you can get wacky stuff. So basically what do we have? The sum of the forces X equals mass times AGX, the sum of the forces Y equals mass times AGY. This is translational motion. This is what we've been doing all semester. And this is now, we're applying all of these accelerations to the center of gravity. And since we weren't rotating, then the acceleration here, the R omega squared is, and the R alpha is 0, right? Because we're not rotating, so there's no alpha and there's no omega, and so therefore the acceleration at every single point is 0. What has to happen? Well, these forces are going to apply a moment about the center of gravity, which needs to be countered by the other moments, so that when we add up all of our moments, we get 0. It's back to a statics problem. So the statics problem is still the same, but now we have some of the moments about the center of gravity is equal to 0. But if we take our moments not about the center of gravity, then we have a more complicated problem. Right? So the sum of the moments is the sum of the r cross f's plus the sum of the moments. What's that equal to? Well, it's IG. What is IG? This is the mass moment inertia about the center of gravity. Plus, now we have r cross ma. So even if we're not rotating angular acceleration, the sum of the moments about any point P is not equal to 0. It's equal to this, and then what is this r cross ma?
R cross the force.
Well, this looks a lot like r cross f. And so this term here is the moment you get if you would treat your mass times acceleration like a force. You would have a moment about the point P. So the moment in the x, the moment due to the acceleration in the x, what's the moment r? Y bar. Moment about the acceleration in the y is x bar, but this would give you a positive or negative moment. Way strong. Give you a negative moment, it would cause you to rotate clockwise, and the y acceleration of the x would be a positive moment. So these accelerations would tend to cancel each other out when everything is positive. So the advantage of this is what? Well, if we have a reaction force at P, when we take the sum of the moments about P, it's equal to 0. So we can pick our point P wisely so that we can cancel out some of the unknowns in our equation. So that's the advantage of this equation. What happens if we write our sum of the moments about the center of gravity?
The forces of the...
What is R going to be?
0.
0. So the distance between the center of gravity and point P is R. So if you write your sum of the moments about the center of gravity, then this term is going to 0. And therefore the sum of the moments about center of gravity is equal to IG alpha. How else could we have this term be equal to 0?
Acceleration 0.
Well, the acceleration is 0, but that's not that's statics. We're in dynamics. When is the cross product 0? When they're parallel or in the same direction. So if your acceleration is in this direction and your r is in this direction, then this is also 0. But that we're not really going to use in this semester, but that is also true. So we can take the kinetic moment, so some of the moments kinetic about point P. That's basically, this kinetic moment is what your mass times acceleration would have, the moment that would have about your point P. And we can use that, again, to cancel out reaction forces. And so some of the moments G is equal to IG alpha. Why is that a scalar equation? Well, that was a vector equation. What directions are some of the moments? Of planar motion, it's always in the z direction, so that's why that becomes a scalar equation. In reality, it's a vector equation. When we have a planar motion, then it becomes a scalar equation. So you don't end up with 6 equations and 6 unknowns, you just end up with 3 equations and 3 unknowns if we're in the plane. So we have 3 independent scalar equations. Some of the force is x, some of the force is y. And then some of the moments is equal to IG alpha, or the sum of the moments kinetic equals the sum of the moments. So those are your 3 equations. And you can also do it about a certain point P to cancel out some of your unknowns. Only translation, all of the acceleration is the same. Alpha is equal to 0. And so we basically have the sum of the moments about center of gravity is equal to 0, or we can take some of the moments about a certain point P and do the kinetic moment. So the sum of the moments about point A is equal to the acceleration of point G times the distance from the center of gravity. It's the moment that the mass times acceleration would have about point A. And this is useful for getting rid of reaction force. Curvilinear translation. What do we have? now our acceleration is mass, acceleration, tangential, and normal, pointing to the center of gravity, center of curvature, I mean. So it's v squared over r and v dot. And we could still do the same. We could take the moments of each of these 2 points about point A to calculate our equation. So we have basically the moments due to each of your equations. So we basically want to establish a coordinate system, normal, tangential, x, y, determine the acceleration of g. So it's basically a good way to write the acceleration of the center of gravity. And then the free body diagram and kinetic diagram. So you want to draw your free body diagram just like statics, and then you want to draw your kinetic diagram so that you can get your r cross ma in the right direction. That would be your inertial forces and couples. That's the r cross ma is your couples. And then look at what your unknowns are. And you basically have 3 equations of motion. So the force is x, y, or normal, tangential. And then the sum of the moments you can have either about a point P or point O. And then basically friction forces act always opposing the motion of the body. So picture your body having ice, where you have no friction. What direction is it going to move? And then the friction force will be opposite that direction. So here we have a fine crate. We're going to push on the crate at a height of 0.8 meters. What could happen? We have a couple options of what could happen. We could slide or we could tip over. If you push on it too high, if this is tall and you push on it too high, it just falls over. So those are the 2 possibilities, but judging from the fact that we're talking about translation, we're going to predict it's going to slide, but then we need to prove that we end up sliding. So we have a 50-kilogram crate, so we're happy that we are using the scientific SI, System International. Horizontal friction is 0.2. What we want to figure out is what the acceleration of the crate is if P equals 600 newtons. So let's get rid of this xy. So we draw a free body diagram, and also we draw our kinetic diagram. So this is equal to this. So we have square is equal to square. What are the forces acting on our crate? Well, one given to us says this is 600 newtons, and this is a height of 0.8. And then what else do we have? We have friction. And we also have gravity. So we're going to have gravity. And then where's our normal force? Well, when this is tipping, where is our normal force? It'll be, when it tips, it's going to be around this corner. And so what we can do, a little different from what the book does, we can call this point A and this point B. So here we have NA, here we would have NB. And when do we tip? When NA is equal to 0, then we know we're going to be tipping. If NA is negative, then we're tipping. So we have, if when we solve our equations, NA is less than 0, we tip, and then we have to go through and resolve all our equations again. And so then we're going to have it's mu k and b and mu k times NA. So our friction force is going to be, we'll have a friction force at A and a friction force at B. In reality, we're going to have like a distributed force, but that's too hard to deal with. So in reality, it would be distributed force at some sort of angle.
Is that what the book does?
That's not what the book does. What the book does is they assume a force and a distance. So you can combine these two into a force and a distance, which would have the same total and would have the same effective moment. Those are 2 different ways you can go about solving the problem. So that's our free body diagram. We were assuming that we're reacting at both A and B, and then if NA is 0, we're going less than 0, we're going to be tipping. And that's equal to what? Mass times acceleration. So we still have the sum of the forces equals mass times acceleration. This mass times acceleration is always going to be located at the center of gravity. And so this was 1 meter. And this was also 1 meter. So this distance here is 0.5 meters. And this height here is also 0.5 meters. So, equations of motion. That's our free body diagram. What do we have? We need to establish a coordinate system. X, Y seems to work well for this because everything is either vertical or horizontal. So we have the sum of the forces X equals mass times acceleration in the X direction. What are the forces in the X direction? 600 newtons minus mu K and A minus mu K and B. So that's this, and this is equal to mass times the acceleration. The acceleration is one of the things we're trying to find as we're going along. So again, we're assuming we're going to slide, and then, all right, so then we have the sum of the forces Y is equal to what? That's equal to mass times the acceleration to Y, which is equal to 0 because we're moving horizontally. So this is what? Here we have positive to the right, here we can have positive up, so this is equal to minus mg plus na plus nb, and this is equal to 0. So from here we can say that NA plus NB is equal to mg. That is the total vertical force is equal to 0. So therefore this is equal to 600 newtons minus mu, which is 0.2 times our mass, which is 50 kilograms, times G. What did I use for G? G is 10. Just to make our life a little easier. So what's that equal to? So we basically have 50 times A is equal to 600 minus 100 is 500 newtons. Therefore, our acceleration equals 10 meters per second squared. So that's our acceleration. And we didn't need to fit, so that's our acceleration. And that's exactly the same as we had in chapter 13. Now, are we going to tip? How do we figure out if we're going to tip? So we have unknowns of NA and B, and now we know A. So how do we figure out if we're going to tip? We need to figure out what NA is going to be. So where do we want to take our moments about? At point B. So if we take our moments about point B, then that removes the other unknown about the equation. So we have the sum of the moments about B is equal to the sum of the moments kinetic about B. Some of the moments about B. What's it? B is such a wonderful point. Why is B such a wonderful point? Well, B goes away. UKB goes away. UKA also goes away. So we're getting rid of a lot of our things. We basically have NA, 600, mg, and A. So the sum of the moments about B is equal to mg times 0.5 meters. Is this going to be a positive or a negative moment from gravity?
Positive.
Positive. And then we also have 600 newtons times 0.8 meters. Is that going to be positive or negative? Negative. You guys are so good. And then we also have a normal NA times 1 meter. And that's also going to be negative. And this is equal to what? It's not 0. Because now we're taking it about B, this is going to have a moment. So this is going to equal mass times acceleration times 0.5 meters. Is that positive or negative? That is also negative, because we're doing it about point B. It's going to cause us to rotate clockwise. So plugging in our numbers, we have 50 times 10 times 0.5. This is meters per second squared. This is kg, 0.5 meters minus 600 newtons, 0.8 meters minus NA times 1 meter equals minus 50 kg. Your A was 10 meters per second squared times 0.5 meters. So from here we can solve that NA is 20 newtons. Which means what? Therefore we're not tipping. NA greater than 0, therefore slide it. If we found out we were tipping, then we don't know what to do yet. We have to go to the next section in the book, which is 17.4, to figure out how fast we're going to be tipping. So we didn't slide. So what do we have? Let's see if we got the concept. This is dealing with friction. We're just looking at our free body diagram. We have a disk at A that has 2 pounds, and it rolls without slipping. What's the correct free body diagram going to be? So we're only looking at the free body diagram. We're not looking at the kinetic diagram, because we don't know how to deal with rolling yet. But we're just conceptually, which direction is our friction force going to be?
So that's B falls and A rolls.
B falls and A rolls. And point B is massless.
So I'm guessing part B with 8 pounds is supposed to be 6 pounds.
What? No, part B, we basically stick both of these together at the middle.
Josh Hackman?
Yeah.
You said you're dead. So you get new batteries.
Let's see. There's some Translational batteries right here. Now it's not secret anymore.
Thank you.
Well, what usually happens is if you replace 2 batteries,
yeah,
it dies quickly.
That is a secret.
All right, we able to vote? We're good to go? All right. So, I guess more than half of you got it right. So it's either A or C, right? Because there's going to be friction. Now, if this was on ice, what would happen?
No friction.
There'd be no friction. So this link would push where? It would be pushing in the middle. So you're pushing the middle to the left. What direction is the bottom going to be going? Also to the left. So therefore, the friction force is going to have to be pointing the opposite direction we're going, which is C.
I thought it was a rolling wheel.
Yeah, it's not rolling. It's not ice though, and it's not slipping.
So which way? So as I said at the beginning,
this way. The motion would want to go to the right, to the bottom of the wheel.
all right. Fortunately, we have a wheel handy. We don't have a nice flat surface.
The wheel opposes friction.
Right. So if
Because if it's spun out like a car that spins out.
how does the car spin out? What's applied to the wheel? What forces? To spin out, you also need to apply a torque about the middle. So if we were spinning out, then on ice the wheel would spin, and the friction would actually point you the direction you're traveling. That's why cars work.
Right.
But the front wheels, there's no moment. You're just applying the center force, and so what? The wheel rotates. Well, what's going to cause the wheel to go like this? Friction pointing the opposite direction of motion. So that's how we get here. The friction is going to be against the opposite direction of motion. If we had a motor, then this would be the right answer. But we don't drive on ice enough in California to easily visualize this. So C in our case was the right answer. Okay, now we slide.
Now we slide.
You're rolling with slipping. What's the correct free body diagram? That's the previous. All right, let's finish this up. 5, 4, 3, 2, 1. All right, it's still the same. Friction acts the same way either way. Whether you're slipping or not slipping. How do we figure out how it happened last time? We assumed it was slipping. What direction is friction going to go? Well, now we are slipping, and the friction is still the same as before.
So, that kind of confused me what you were saying about the wheel. As in the friction, if you have torque, your friction is in the forward direction.
Yeah.
The direction of motion.
Yes.
That's only if you have torque.
Yeah.
Always, otherwise, the friction is always the opposite direction of motion.
Yes. So if we apply torque, then we have ice. What direction does the bottom of the wheel go? The bottom of the wheel is going to the left, and so therefore we would apply a force to roll that way. If we push this, then friction is going to oppose motion this way. Because then we don't have a motion, so it wants to slide, but then the friction would cause it to roll. So the difference in this case, what's the magnitude of Fs? We don't know. This is one of our unknowns. But we know that the velocity here is 0, and so the velocity of the center is going to be r omega, the acceleration of the center is going to be r alpha. So if we're rolling without slipping, we know the relationship between the acceleration and alpha. If we're rolling and slipping, then we know what the force of mu k and mu k is. So we know our forces, and we don't know A, and we don't know alpha. And we'll see that in next lecture, 35 minutes. We probably want to do this as a group. So we have our cart. We're pushing down on our cart like this. And what we want to figure out is what are reactions at A and B. We're pushing down on the cart. What are we worried about?
Flip up.
It's flipping up, right? We're pushing down. And this force is not between the two wheels. And so we do have the potential that we can flip our cart. And so the sea monster, is that sea monster? Whatever's in our cart is going to make a mess. So, how do we solve this problem? Free body diagram! Right, so follow the procedure, free body diagram. So what we have we know our free body diagram and also our kinetic diagram. So our cart, we have a handle. So we have an A and B and P going down at an angle of 60 degrees. And we're neglecting the mass of the wheels. What does neglecting the mass of the wheels mean? There's no moments, there's also no reaction force, there's no friction force.
There's no resistance to rotating the wheel.
Well, the wheels are massless, and so we have, what was it, some of the moments is equal to I alpha. Well, if I is 0, because we're massless, and the sum of the moments equals 0, so therefore there's no horizontal force. That's basically what that's saying. That'll become clearer later on. But basically that says that there's no horizontal force, there's no friction force. Last time we had wheels were 2 pounds, and so they weren't massless, and so therefore it takes an effort to get our wheels rotated. Now we have massless wheels, so it doesn't take any effort to get them going. That is that the mass of what's ever in our cart is a lot more than the mass of our wheel. So this is 50 pounds. So those are our forces, right? Or 50 newtons. Okay. Are those our forces?
Weight.
We also need our weight. So we also have mg, which is equal to, what do we have, 200 kilograms? Times 10 meters per second squared, just to make gravity a little easier in our equations. So now we have all of our forces, and that's equal to what? Mass times acceleration. So we have mass times acceleration. What? Oh, it probably goes to the left. That's probably a good assumption. We're pushing it to the left, so I'll assume. What would happen if we assumed it moved to the right? We get a negative number, and that's fine. This is obvious which way it's going to go, so we might as well get the positive answer.
Equalizer, can we call that positive?
We can call whatever direction we want positive.
Well, we have.
What? We're going to have.
Well, I mean, like, we said it's going that way.
Yeah, then this is positive, but if we take positive when we write our sum of the forces and the x is right is positive, and this would be a negative and that would be a negative, and we negative, and then we cancel out, and it'll work out.
So, in this circumstance, doing the kinetic diagram is the main purpose of it is to find the distance from.
Yeah, it's to figure out what the sum of the moments, the kinetic diagram in our case, when we're not rotating, is basically finding the distances for this moment.
Okay.
Is what we need to do. And so what distances do we have? This distance, distance is 0.3 meters. This distance is 0.2 meters. What other distance we have? This distance is 0.5 meters. And this distance is 0.4 meters.
Up from the wheel to the G.
Is it from the wheel to G?
Or the height of
Oh, and we also have this distance here, which is 0.2 meters. Okay, that's what you were saying. So this distance here is 0.2 meters. Okay, so what are we trying to find? NA and B. So how do we figure that out? Sum of the forces, so we have sum of the forces X, where we're going to call positive to what? To the left? To make us happy?
Yeah.
Equals mass times AX is equal to what?
P cos theta.
So it's P, so it's 50 newtons times cosine of 60 degrees. That's equal to 200 kg times A. And so therefore, what do we get? A is equal to, I didn't calculate it, 25 over 25 over
1.125.
what, 0.125?
Yeah.
Meters per second squared. Why didn't I calculate it?
Maybe. Yeah, you do need it later.
Where's your happy point?
That will be
What did I find? We found NA. So,
center.
here's a happy point. Why is this point happy?
Because NB is gone.
Because then we can get rid of
NB is gone,
And MA.
and MA is also gone. They both pass through point P.
Maybe that's why you didn't calculate A.
That's why I didn't calculate A, because it turns out we don't need to if we pick our point wisely. I've done this before, so I knew to do that. So this is true, this is our acceleration, but we didn't need to find the acceleration. So what we can find, what? It wants NA and NB. It never asked us for what A is. So if we would take our moments about here, why did we take our moments about the ground last time?
Get rid of one of those.
To get rid of these evil friction forces. But now since we don't have the evil friction, they're not evil, but because we don't have the friction forces, now we could pick a point up here to get rid of another one of our unknowns. So we have the sum of the moments about P is equal to the sum of the moments kinetic about P is equal to what? Well, what are the sum of the moments about P? We're going to have NA times 0.5 meters. Is that positive or negative?
Negative.
Negative. And then working our way, we're going to have mg, so it's 200 kg times 10 meters per second squared. Is that positive or negative?
Positive.
It's about point P, so it's positive. And I forgot something. That's our force times the moment arm, which is 0.2 meters. Okay, and then NB goes away. Now we have that P.
Oh no.
So yeah, it's easier px and py makes our life a lot easier. So this is py, this is px, which is equal to p, it's equal to what? 50 cosine 60 degrees, and this is 50 sine 60 degrees. So that will make our life a lot easier. And that's equal to what? So it's that, and then we have plus 50 cosine 60 degrees. That's the force times the distance is 0.3 meters. And then we have 50 sine of 60 degrees times what distance? 0.4 meters. That is positive or negative?
Negative.
It's going to be negative. That's equal to 0. Because the mass times acceleration is going through our magic point P. So the R cross MA is 0. And so when we do that, we can figure out that NA is 780 pounds? Not pounds. I have an N on my paper. And then what do we have? What other equation can we use? Sum of the forces what? So this is, and then we'll go positive up. And so sum of the forces in the y is equal to NA plus NB minus MG minus 50 sine of 60 degrees. This mg was equal to 2,000 newtons, and A was 780 newtons plus NB. And then, oh, sorry. We're halfway. That's the sum of the moments. This is equal to what? 0, because we're not accelerating vertically. This is minus, and this is minus 50 square root of 3 over 2 equals 0. So we can get that NB equals 1263 newtons. So why doesn't NA plus NB equal to the weight? Because we also have this dy pushing down. That's why it doesn't. But yeah, so we could have, what was the other? We could have some of the moments about the bottom, but then we would have this 0.2 times MA. So that's what we would need our acceleration right there. We also could have taken some of the moments about this point right there to calculate B, but that would be a lot more complicated than just doing the sum of the vertical forces once we had the vertical forces. All right. Whee! Last question. So this linkage is actually undergoing curvilinear translation because this length is the same as this length here. So this is like the school bus problem, the school bus amusement park ride, where this is staying flat. So if that's the case, how many independent scalar equations of motion can be applied to box A since it's going in curvilinear translation? So we're now doing question 2. Question 1 was D, was the answer. All right, 5, 4, 3, 2, always end up with 3 equations of motion.
Unless it was 3D, right?
If it was 3D, then, yeah, then we would have 6.
Now you look at it.